In this video, we're going to derive a formula that relates the change in velocity, that is VF minus VI, to the change in mass. Now that's the change in mass of the rocket plus fuel, so really it's just the amount of fuel that's consumed. The final mass minus the initial mass, that total difference is just the fuel that's consumed in the ignition process. So the formula that we're actually going to derive, I'm going to put it down here at the bottom so we can have a target, something to shoot for. The final velocity minus the initial velocity is equal to the log of the initial mass over the final mass times U minus G times del T, where del T is the amount of time that the rocket engine is fired. So over here we see a 1 that says yes, this is true. And again, I've derived all these formulas ahead of time and set up this page so that all these formulas will be true. That way we can check our calculations. If ever we get to a point where we don't see a 1, then we got to think about it. Maybe something's wrong. So how are we going to derive this formula? Well, we're going to start the same place we did before by referencing our conservation of momentum principle, and that is m times v minus m times g times dt equals, and now we got to express the momentum of the whole complex in terms of its two pieces, and we did this in the previous video. That's going to be this reduced mass times the increment in velocity, that's one piece of the puzzle, plus the mass of the fuel burnt times the velocity of the fuel burnt. And again, it has to be V minus U because we want to express everything in terms of the velocity that an observer on Earth would see. And we see a 1 there, so that means that's good. We're on target so far. Let me give it some more decimal places, just so you know if we're a little off from one, if our equations are a little wrong, it'll show up in that slot there as maybe 0.99 or something. But so far it looks like we're okay. So now we're going to take this equation and we're going to manipulate it somehow and end up with this equation. So let's jump in here and hope we come out okay. Let me put my pieces in locations where I will not be covering up too much. Okay, so as before, I'm going to get rid of my absolute values by clicking on that little conditional operation over on the right here. Then I'm going to expand my terms and do pretty much what I did before. I have an MV on both sides of the equation, so I'm going to get rid of that by going to my auxiliary slot, putting it in there, and subtracting it from both sides. Now, notice this piece here, dm dv. I'm going to handle that a little differently this time. Remember, we have a double differential we saw in the previous module, the previous video, that when we go to the derivatives, or we let dt go to 0, that's going to disappear. So in this case, I'm going to just get rid of it up front so we don't have to deal with it. So I'm going to go substitute for that dm dv, and I go to my substitutor, and notice it is 0, and as dt goes to 0, it'll become even more 0. If I were to look at some more decimal places there, eventually you'd see something non-zero, but then I just decrease dt until you saw 0. So that in the limit is going to be 0. So I'm going to make that substitution right now. All right. Now what do we do? All right, we want to solve this differential equation, and we're going to do it using a technique called separation of variables. Remember what's dependent here. G is a constant. G is a constant. M depends on T, so it's a variable, so we got to be careful with that. And of course T depends on T, and U is a constant, so we don't have to worry too much about that. So if we're going to use the principle of separation of variables, we have to get terms in here that only depend on one changing variable. And the problem is this here. We can't use separation of variables on this term because it has an M and a T part, and how do you integrate that? You got to get it just dependent on M's or T's, but not both. So how are we going to do that? Well, we're just going to divide through by M. So I go up here, I put M in my auxiliary slot, and I divide through. Okay, now if we look at all our terms, this first one, it is just dependent on T and the constant G. So we don't have to worry about constants. That's okay. And then this one here is dependent on M and the constant U. So our variables are separated, as we call them in the world of differential equations. And this one here is just a V. It doesn't have any M term in there, so we're in good shape there. So we've separated our variables. So now we can just integrate both sides. If we do that, and the program should do that automatically, when we integrate dv, we just get v. The integral of dv is v. That's the integral of 1 dv is what it really is, and that's just v. And the integral of g dt is really the integral of 1 dt, which is just t. So those are pretty simple. And this one here, dm over m, that's one you have to remember. The integral of dm over m is the log of m. So the program knows all of that, I hope. So if I just do the integral, it'll give me those transformations. And like I said, there's the gt, there's the v, and there's the log of the absolute value of m. Since m is always positive, I can get rid of that absolute value sign. And notice it throws in some constant. The integral is only defined up to a constant. So the first thing we have to do is to, first of all, let's save this formula because we're going to want to use it again. We have to figure out what that constant is. And the way we figure out the constant is we use the boundary conditions. We're saying that at time t equals 0, its mass is mi and its velocity is vi. Well, since this formula up here is true for all t, it has to be true for that initial condition, so we can plug those numbers in, and that'll tell us what the constant is. So I do a drag and drop. Notice that t equals 0, so that side drops out completely. I substitute for m, mi, and I substitute for v, vi. And then I'm going to just rearrange this. I'm going to solve for some constant. I want to know what that is. I can do that by just doing a solve for. And let's save that. So I now know what the constant has to be for the initial boundary condition to be true. Now let's go back to our general formula and big that. And I make that substitution. So now I have a formula that's true for t and v, so I can actually solve it for v in terms of t and other things. Let's do that. I'll go up here and put, I got to do a right click and put a t in my auxiliary slot and then do a solve. So that's my formula for t, but that's not what I wanted. I want to know what v is in terms of t. So I got to go up here and put a v in my auxiliary slot and do a solve for v. Okay, now I have a formula for v in terms of t. Let's look at this. Here's v on this side. And if you look over here, here is T. And if you look through the rest of this thing, you don't see V in there anyplace. So I do have a valid formula for V. It's not on both sides. I have some pieces that depend upon M, which is the final M, or the M at time T. That's this piece here. That's the M. Remember, M is changing with time. It's a function of time. So this is the M at the final point in time, and this T is the T at the final point in time, or the time that you're interested in, and this V that we're ending up with would then be the velocity at the final point in time. So let's make those substitutions. Let's get rid of our temporary items. So we're saying what is the situation after del T, so let's put that in there for T. And we're calling our final velocity mf, so let's put our final mass mf, so let's put that in there. And we're calling our final velocity vf, so we just put that in there. Now let's rearrange this. So remember where we're heading for. We're heading down here. This is the formula we want to end up with. So we got all our pieces, we just got to rearrange them a little bit. And in particular, this vi, we want to put that on the other side. So I put that in my auxiliary slot, and I subtract it from both sides. Now I want to get this log, this piece here, I want to move it over a little bit so that it's next to the other piece that looks like it. And then I'm going to highlight those two pieces together. If I do a Control G, that groups them together. Remember, the program puts them together however it likes, and sometimes that's now not how I like them. I put them together in this group because now I can do a factor on all terms, and it will factor the things inside this parentheses. In other words, it'll pull that u out. So if I do that factor all terms, one of my standard equation operations, I've factored the u out of that expression. And the reason I've done that is because I'm left with a log minus log, which as high school students of algebra we recognize as the log of mi over mf. So I'm going over here to my conditional operations and doing that. And there it is. That's the formula that we wanted to end up with. If we compare this, I put it down here. These are the same thing except the grouping. I can get rid of the grouping. I don't need that anymore. And put them down there. Formulas are the same. So this says then that in order to compute the change in velocity, you have to look at the log of the initial mass compared to the final mass times u. That's the propulsive velocity. And if you were in outer space with no gravity, that would tell you what the change in velocity is. If gravity is pulling things down, then you have to throw in this g times del t. That's the impulse component. Remember, mg times del t is a change in momentum, so g times del t is just a change in velocity. Alright, I think that's all I want to say about my formula here. So what I've done here is I've derived this formula down here. Let's say we write it analytically by solving this differential equation up here. I want to test that. It's probably right, but I always draw a lot of comfort by going to a simulation that tests these results. And so let's go back to our simulation and see how we can test these results. So we go to our rocket simulation, and let me just fire it off again, and then we'll talk about the results. So here's our rocket taking off, burning fuel. Remember, as it burns the fuel, the mass of the rocket fuel complex is decreasing, and the rate at which it's burning fuel is dm dt. We call that the burn rate, and then the burn rate times the velocity at which the exhaust is being propelled from the rocket nozzle. That product is called the thrust. So let it work it all out, and then we'll show how this simulation tests our formula. Alright, let's go over here and look at these numbers here. Alright, the formulas on the left, or the numbers on the left, are from the formula. If I look at VF, for instance, if I do a big on that, that's the formula that I derived on the other page. That's the analytic solution to the problem. If I look at this number here, if I do a big on that, that's just a number, and that number was generated by the simulation. So the fact that they came out to be the same is a pretty good indication that the formula is right, and that the simulation is right. You know, it could be that one or the other is wrong, but it'd be odd that if one of them was wrong and the other was wrong, and these both came out to be the same. So that gives me some comfort that the formula is right and the simulation is working. Now, why does that make me more comfortable? Well, if we look at the simulation is the crux of it is up here in this action button, and there's a lot going on here, but here is the essence of it. The program has the ability to, hang on a second, the program has the ability to take the differential equation and generate the corresponding motion. So there's not a lot of thought involved there, and it's not, you know, it'd be hard to make a mistake. And what's the differential equation? Well, if you look at this is essentially the thrust. It's the thrust divided by m, which is the acceleration. So what you do with the program is you plug the acceleration into the program, and it generates the motion. So if you get the acceleration right, then the motion is going to be right, and you don't have to do all the additional calculations it takes to come up with the analytic solution. So you're fairly certain that your simulation is going to be right. And then, of course, you make the comparison with the formula. If they come out to be the same, then you're pretty comfortable that you've done things correctly. So I think that's it for my two videos on thrust, and I don't know what we call the second one. This one is how does change in velocity relate to fuel consumption. And let's close this one out then, and the final video will be just something on the quiz, how that can help you remember some of these concepts.